Hi guys, welcome to the series of lectures on applied statistics. In the last lecture, we discussed how to frame the null and the alternative hypotheses. Today, we shall discuss how to settle the arguments arising out of these statistical hypotheses by conducting the statistical hypothesis tests. Specifically, we shall show how to use two very popular tests, that is the z-test and the t-test. So let's start. Hypothesis tests can be of two types, one-sided or two-sided, and it all depends upon how you frame the alternative hypothesis. So if the null hypothesis says that the mean equals 30 and the alternative hypothesis states that the mean is greater than 30, then the hypothesis test will simply check probability of observing the sample mean on one side, that is above the mean value of 30. Likewise, if the alternative hypothesis is that the mean is less than 30, then the hypothesis test will again check the probability of observing the sample mean only on one side, and that is below the mean value of 30. Hence, each of these tests is a one-sided or one-tailed test. If instead the alternative hypothesis states that mean is not equal to 30, then the hypothesis test will check the probability of finding a mean value on either side of 30. Hence, it is a two-sided or two-tailed test. To conduct a hypothesis test, we need something called a test statistic. This is because the whole sample is a large set of values. And to run a test, we need to summarize the data into a test statistic. And this statistic is a parameter of the population. For example, if we have a sample of car speeds, then the test statistic can be the mean value of this sample. Hence, our null hypothesis can be that the mean speed equals 30, whereas the alternative hypothesis can be any of the three inequalities as on your screen. Now, how do we test whether it is time to change our beliefs and accept that average speeds are indeed higher than 30 miles per hour? To do that, we can sample speeds repeatedly and see if we get similar sample means. But that will be a long and expensive process. So what can we do to see the bigger picture? Now here is an idea. We can use the central limit theorem to see the picture without sampling repeatedly. This is because the theorem already tells us that if we sample repeatedly, then the sample means will be normally distributed such that the mean of this distribution is the same as the population mean, whereas the standard deviation equals the population standard deviation divided by the square root of the sample size n. We call this distribution the sampling distribution of the sample means. So what are the population's mean and standard deviation? Well, according to the null hypothesis, the population mean equals 30. Hence, the mean of the sampling distribution is also 30. Next, suppose the population's standard deviation is also known, and say in this example it is equal to 11. So here is how the sampling distribution of sample mean looks like. Now to test, if we accept the alternative hypothesis, we check what is the probability of observing the sample mean as far out as 35 or beyond. We can do that because the area under this normal curve equals 1. Now, if this probability is below a certain threshold, we conclude that if circumstances were as the null hypothesis states, then we have observed a highly unlikely event. In fact, we conclude that this event is so unlikely that is inconsistent with the null hypothesis. Therefore, we reject the null hypothesis in the favor of the alternative hypothesis. The threshold with which we compare the probability is called the significance level, or alpha. Note, often we use standardized sampling distributions. Hence, here on this slide, the mean has shifted to 0 and the horizontal axis plots the normalized sample mean represented by the variable z. If you want to refresh your memories on how to standardize a normal distribution, a video link is given in the description under this video. The portion of z-axis under the shaded part is called the critical region. If our observed statistic, that is sample mean in this case, falls within the critical region, we reject the null hypothesis H0. The start of this critical region is also called the critical value, and it is marked by Z alpha. The significance level alpha represents the shaded area under the curve. Typically, it is 5%. Alpha is shaded as per how we framed the alternative hypothesis. Here, the alternative hypothesis checks if the actual mean is greater than the mean under null hypothesis, that is mu naught. Therefore, the observed sample mean must fall in the right or upper tail of the normal distribution. If instead the alternative hypothesis contends that the actual population mean is below mu naught, then the critical region is in the lower or left tail. However, if the alternative hypothesis is that the actual population mean is not equal to mu naught, that means it can fall in either extreme. Thus, the critical region is split into two halves on either side. This is shown by alpha divided by 2. So the top two tests represent the one-sided or one-tailed tests, whereas the bottom test is a two-sided test. Can you guess the consequences of using a two-sided test? Notice, because the significance level is split in halves on either side, to pass the two-sided test, the observed test statistic must be more extreme than in a one-sided test. Therefore, a two-sided test is harder to pass. However, if we want to measure the effect of an intervention that can impact either way, we must not give in to the temptation of using an easier test. For example, a drug may influence the health both ways due to possible side effects. Therefore, to prove its efficacy, it may be better to use a two-sided test instead of just a one-sided test. Therefore, in our statistical analysis, we must always state the type of test and justify its use. So here's an example comparison between the two kinds of test. Suppose we test whether the mean speed is greater than 30. The sample mean from a sample size of 50 equals 32. You can compare the critical regions for one and two-tailed tests from these pictures. Can you guess the critical region for the one-tailed test? To do that, you must look at the top figure, and I'm sure you guessed that the critical region begins at 31.8. Thus, a sample mean of 32 means we reject the null hypothesis. If instead we use a two-tailed test, then the critical region begins at 32.2. Because the sample mean was only 32, we failed to reject the null hypothesis in this instance. We can also test a statistical hypothesis by reporting the p-value. If we assume that the null hypothesis is true, as we do at the start of every hypothesis test, then the p-value is simply the probability of observing a value as high, low, or extreme as the sample value of the test statistic. So suppose capital X is the test statistic and the small x is its observed value. Then the p-value is the probability of finding at least as high a value as the observed value for a greater than test. Likewise, the p-value is the probability of finding at least as low a value as the observed value for a less than test. In a two-sided test, the p-value is the probability of finding a value as extreme in either half of the distribution. Therefore, the p-value is the sum of two probability values. Let's demonstrate that with some examples. Suppose the significance level alpha equals 5% or 0.05. Here we assume a standardized distribution with a mean 0 and variance 1. We want to test if the actual mean is less than 0. Well, the observed value of the sample mean is minus 1.93. The corresponding p-value is 0.0268. You can compute that in R using the p-norm function as shown on your screens. Since it is a standardized distribution, default values were assumed by the p-norm function. Note, as the bottom figure shows, this p-value is the probability of seeing values minus 1.93 and below. It is not simply the probability of seeing a value of exactly minus 1.93. As the p-value is less than the significance level of 0.05, the null hypothesis is rejected. Let us now reverse the situation and test whether the mean value is greater than 0. So the observed value is 1.93 in this case. Note the p-value is still the same as before. Are you surprised? You shouldn't be, because the situation is the mirror image of the last situation. Therefore, while using the p-norm function, we omit the probability of finding all the values less than 1.93. Again, the p-value is less than 0.05, and so the null hypothesis is rejected again. Now consider a two-sided test. So the significance level is divided into two halves on either side. This time we test if mean is not equal to 0. Again, the observed value is the same as before, but the p-value is doubled this time around. This is because we want to cover the possibilities of finding a value this extreme on either side. But notice this doubling raises the p-value above the significance level of 0.05. Hence, the null hypothesis is not rejected this time around. Hence, you can see that passing a two-sided test is harder. So let us summarize it now. We will assume a standardized normal distribution here. Suppose the central limit theorem applies. That means the sample size is large enough and the population's standard deviation is known. Then we can standardize our sample mean as shown on screens to compute a z-score. Here x bar is the observed sample mean, mu is the population mean under the null hypothesis and equals some value c, and sigma x bar is the standard deviation of the sampling distribution of the sample means. According to central limit theorem, it equals sigma over square root of small n. Now, if we want to compute a one-tailed test and we are checking for a decrease, then if alpha equals 10%, then the critical value is minus 1.282 and its p-value is 0.1. Thus, we reject H0 if we observe a p-value below 0.1. You can use the Q-norm function in R to compute the critical values corresponding to a given p-value. At alpha equals 10% or 0.1, we can use Q-norm to find the corresponding value, and that will be minus 1.282. The most popularly used value of alpha equals 5%, and the corresponding critical value equals minus 1.645. It shows greater significance if we lower the alpha down to 1%, and in this case the critical value equals minus 2.2326. If instead we want to conduct a one-tailed test for an increase, the critical values and corresponding p-values are on screen. Notice the magnitude of the critical values is still the same as before, only their signs have reversed. However, in a two-tailed test, the critical values get pushed further into extreme on either side. So because we are using z-scores or a z-statistic under the assumption that the central limit theorem applies, we name the test as z.test. So suppose we have selected a sample x, then x bar equals sample mean. We can standardize it by computing the z-score as on your screens. Notice mu equals the population mean under the null hypothesis, and x bar is the test statistic. Assumptions for the z-test are the same as that for a central limit theorem. That is, the values in the sample are independently selected with replacement. The standard deviation of the true population is known, and the population is either normally distributed or the sample size n is large. Typically, this means 30 or more. At this stage, I invite you to write a simple function in R called z.test that computes the z-score given a sample of values, the population mean and the population variance. So here's an example of the use of z-test. The data comes from a study in 1902 about 3,000 male prisoners. The research question is if the mean height of the male prisoners is different from the assumed average of 66 inches. The population here corresponded to all the male prisoners at that time, and the standard deviation and the assumed population means are given on screen. A sample of 3,000 heights was collected, and mean value in this sample was slightly less than 66 inches. So can we apply the z-test? Well, here are the steps to apply the test. The null hypothesis states that the mean height equals 66. The alternative hypothesis simply tests whether that is true. Hence, it is a two-tailed test. The significance level was set to 5%, and therefore the critical values of a two-tailed test are plus or minus 1.96. Due to the popularity of 5% significance level, you will see the mention of 1.96 quite often in statistics. So to apply the z-test, we must standardize the observed test statistic. So all we have to do is go back to the last slide and find the values to substitute in these formulas on your screen. Hence the standard deviation of sample means, that is, sigma of x bar equals 0.0469, whereas the sample mean x bar turns into a z-score of minus 11.30064. Now since it is a two-sided test, we can consider either extreme value. And because we have generated a negative z-score, we compare it with the negative critical value of minus 1.96. The z-score beats the threshold easily. So there is enough evidence to reject the null hypothesis in the favor of the alternative hypothesis. So we can say that the mean value is not 66, but can we say more? Well, since the z-score is negative, it implies the observed mean value falls in the left tail, and therefore the evidence suggests that the mean value is less than 66 as assumed under the null hypothesis. This shouldn't surprise anyone because the observed sample mean value of 65.47 was also less than 66. Note, however, the null hypothesis was rejected even though the sample mean of 65.47 was only fractionally smaller than 66. Why do you think the null hypothesis was still rejected? Well, note the sample size was 3000, and that is quite a large value. Small differences over large sample sizes do allow rejecting the null hypothesis. Later, we shall see what happens when the sample size is much smaller. We can also report the p-values of the observed z-score. Because it is a two-sided test, we take the probability of finding the observed score, but then we double it because we must also consider the probability of seeing something as extreme in the upper tail. The formula to find the probability in question in R is p-norm. Again, we do not state the mean and standard deviation, so the default values of the Z distribution are used. And the answer turns out to be an incredibly low value, to the order of 10 to the power of minus 30. This is much lower than the desired significance level of 0.05. Hence again, we reject the null hypothesis. Notice the smaller the p-value, the greater is the significance of the hypothesis test. Therefore, it is useful to report the p-value in the statistical reports. Z-tests assume standard deviation of the original population is known. When it is not known, we use t-test, which relies on a t-statistic. The t-statistic, as shown by the formula on screen, follows a student's t-distribution. Here S equals sample standard deviation. This replaces the population standard deviation. Notice for each sample size there is a different t-distribution. In fact, sample size minus 1 is called the degree of freedom of a particular t-distribution, and it defines that t-distribution. The students' t-distributions resemble a normal distribution except that they have heavier tails. Let us see what that means. Let's examine t-distributions with different degrees of freedom. In all the graphs I shall show here, the true normal distribution is represented in blue. So in the first picture, we compare the normal distribution with a t-distribution with degree of freedom equals 1. So you can see fat or heavy tails of the t-distribution. These heavy tails show larger variance. Clearly, if your sample size is small, that is 2 in this case, you must expect a lot more variability. The next picture brings in degree of freedom equals 2, in addition to the curve corresponding to degree of freedom equals 1. So notice you have 3 curves here. And notice the gap with the normal distribution has decreased. Next, we bring in df equals 3, and it approximates the normal distribution even better. In this way, as we bring in df equals 5, and df equals 10, and finally df equals 30, the t-distribution gets very close to a normal distribution. So with this background, the t-test assumes that the samples are taken with replacement, independently, and from the same underlying probability distribution. hence the word IID. Furthermore, the underlying population must either be normal, alternatively, the sample size must be large, that is, at least 30. Since t-distribution is different for each sample size, we cannot list down single critical regions. Instead, one must use t-tables or use a software like R to conduct the t-test. Now let's conduct a t-test, this time on the prisoner data. Again, the research question tests if the actual mean height is less than the assumed height of 66 inches. Notice this time the population standard deviation is not available. So can we apply the z-test? No, instead we must use the t-test because the sample size of 300 is large enough, though it is smaller than the sample size of 3000 last time. Although we do not have the whole sample here, we do have the sample's standard deviation and the sample mean. And the sample mean is 65.78 this time around. So we frame our null hypothesis, that is the mean height equals 66. The alternative hypothesis disputes the null and is a two-sided test again. The significance level is 0.05. The critical values will have to be drawn out for both the tails from the t-distribution with a degree of freedom of 299. That is sample size minus 1. As we substitute the values as before, we get a t-statistic of minus 1.45. If we compute its p-value for the given degree of freedom, it is 0.073. Because it is a two-sided test, we double the p-value and it turns out to 0.146, which is clearly greater than the significance level of 0.05. Hence, the null hypothesis cannot be rejected this time around, unlike the last time with z-test. The difference is simply not the t-test, but also the fact that this time the sample size of 300 is much smaller than the previous sample size of 3000. We can also compare the observed t-statistic of minus 1.45 with the critical values, and that is minus 1.97 for the lower tail. Minus 1.45 is greater than minus 1.97, and hence the null hypothesis cannot be rejected. In R, look up the qt function to generate the critical values. Notice if you want to use the t-test in R, look up the function t.test. However, that function requires you to specify the complete sample, which you do not have in this example. Therefore, I have coded up a new t-test function and put it in the description of this video that works when you only have summary statistics, like in this example. Now suppose you want to check if a class's scores on a stats exam improve after taking a course on statistics. Or you wish to check if the present population of birds at various places has increased since last year. Then you need two samples of before and after scores. And the members in these two samples are paired. For example, score of each person in a class before taking a stats course is paired with the score after taking the course. Likewise, you can pair the population in an earlier year with the population the next year. So there's always a before score and an after score. Each member of the pair links with the other member. Then the research question in all such scenarios is, are the after scores higher, lower, or different from the before scores? For this, we use a variation of t-tests that is called the paired t-test. Here the test statistic equals mean of differences. That is mean of after score minus before score. In a paired t-test, the null hypothesis is that the mean difference of before and after scores equals 0. Hence, there is no difference. The alternative hypothesis can be any of the three possibilities. Thereafter, we apply a standard t-test as before, and the assumptions of the t-test apply. In some situations, the two samples cannot be paired. They are independent. The value in one sample has no link with a definite value in another. For example, if we want to ascertain the mean weights of wild and domesticated animals, clearly the weight of one specific wild animal cannot be paired with that of a specific domesticated animal. In such cases, we treat the samples independently and label one of them as sample 1 and the other as sample 2. It does not matter which sample is labeled what. As before, either the samples must be large or they must come from normally distributed populations. And the null hypothesis is again that there is no difference in the means of the two populations from which the samples are drawn. If such conditions hold, then the difference of sample means is normally distributed such that the mean value is the difference of two population means and the variance is as shown on the screen. The sampling distribution here is the difference between the sample means. If the population variances are known, then we can use the z-statistic, where the z-statistic is as on your screens. Notice if you are wondering what is mu1 minus mu2, then that equals 0 under null hypothesis because the null assumption is that there is no difference between the means. So this expression, the last expression on your screen, simplifies. If instead the variances of the two populations are not known, then we used the two-sample version of the t-test. Again, the null hypothesis assumes that the population means are the same, whereas the alternative hypothesis assumes some inequality in the mean values. The degree of freedom for the test equals size of sample 1 plus size of sample 2 minus 2. Thereafter, we conduct the test for a given significance level. The assumptions of the two-sample t-test are again that the differences of the sample means are normally distributed or that the sample sizes are large. Notice the t.test function in R handles both the two-sampled and paired t-tests. For example, here is a sample call to a paired t-test. Here both the data samples must be of the same size or you will get an error message. Likewise, this is a call to a two-sample t-test, and here the data samples are of different sizes. Finally, here is a simplified scheme for choosing a test. First of all, how many samples do you have? If the answer is 1, next check if you know the population standard deviation. If the answer is yes, choose z.test. Otherwise, choose the t-test. If instead the number of samples is 2, then check if it is paired data. If yes, go for a t-test. Otherwise, go for the two-sample test. With that, we conclude this lecture and we'll see you in the next one. Goodbye.